Welcome back to Lesson 1, Equation of Lines in 2-space and 3-space. We're going to look at the scalar equations of lines in 2-space, then we're going to move that to 3-space. So here we go. Consider the line 4x plus 5y plus 20 equals 0. First of all, it says to graph the line. How do I graph it? Well, I'm going to graph using the x-y-intercept. So x-intercept, set y equals 0 and solve for x. So 4x equals negative 20. I brought the 20 over, set that to 0. So x equals negative 5. So I've got this point here. The y-intercept set x equal to 0, so I've got 5y equals negative 20. So y equals negative 4, so I've got this point right here. Once I got those 2 points, I'm going to draw a line that goes straight through there. There we go. Part B. Determine a position vector that is perpendicular to the line compared to the scalar equation. So perpendicular. So again, what I can just do is take the a and the b value. So position vector perpendicular to it would be 4, 5. And if I graph that, we can see where's 4, 5, there it is. If I move it over here, we can see that they are perpendicular. All right, leave that there. A normal to the line, L, is a vector n called a normal. It's perpendicular to the line, so line ax plus by plus c equals 0, then the normal would be AB. We've already written that down, but there it is again. Now this is a bit tricky. Write a vector equation of the line. So a vector equation of the line, what I need is two things. I need a point on the line, which is, I can use that, and that would be my r naught. And then I need a direction vector. So what I'm going to do is I'm going to take this, I'm going to drag this, I'm going to make this, draw this line right here. I'm going to use that as my position vector, and then I'm going to move him here. And so what is that position vector? I can see that, or sorry, what is that direction vector? I can see that the tip is right here at that point, 5, negative 4. So write this as a vector equation. So xy is equal to, my r naught is negative 5, 0, plus t, and here we go, 5, negative 4. Now another way to solve this, if I wanted to, I could find, using these 2 points, this one, my r naught, and this point here, I could find that vector there. And again, if I did this, so this is the point negative 5, 0, this is the point 0, negative 4, and if I found the direction vector between those 2 points, this would be 0 minus 5, that is 5, and negative 4 minus 0, that is negative 4. So I could have done it that way as well, or I can draw it like that. Either way is fine. We're not always going to have the luxury of having this graph here, so it's probably best to do it like this, and that again will give us that direction vector, or vector m. Alright, vectors in 3-space, so here we go. By the way, there are infinitely many normals to any one line. In 2-space, all normals are parallel. However, this is not the case in 3-space. Very interesting. Now, vector equation in 3-space. This is wrong. That's embarrassing. It should really be x, y, z is equal to x naught, y naught, z naught plus t, m1, m2, m3. So notice there's that extra coordinate there, but same thing, still a vector equation, just adding that z coordinate. So we'll do a few examples in this, and then we'll be done the lesson. All right, first one. A line passes through the points A and B. Write a vector equation of the line. So again, I can use either of these guys as my r naught. I'll use this guy here as my r naught. So I'm going to have here x, y, z is equal to my r naught, 2, negative 1, 5. Again, I could have used 3, 6, negative 4, doesn't matter. But now plus t, and now I need my m. My m vector is just equal to my position vector AB, which would be equal to, terrible form here, Mr. Wills, equals. Just running out of room going down, so I'm going to do it like this. So AB would be 3 minus 2, so 1. 6 minus negative 1, that's 7. And then negative 4 minus 5, that is negative 9. There we go. So this is my M, so I'm going to write it here. 1, 7, negative 9. Again, it is just this guy here is just my vector AB. Part B says write a parametric equation of the line. All right, so here we go. I'm going to have this. I'm going to have L1. So it's basically this just written in columns is equal to, and I'm going to have three things. X is equal to y is equal to, and now z is also equal to. By the way, I made a small mistake here. There shouldn't be equal to here. It should just be L1 is defined by that. All right, x is equal to, look here, 2 plus t. I just took this plus 1t, which is just t. Y, so I look at the middle here, negative 1 plus 7t, and then z, 5 minus 9t. So again, these two things are similar, just written in different ways, but you can still pull off the point, right? This guy right here, there's my r naught, and this guy here, this is the coefficients are my m. All right, next one says here, determine if the point C lies on my line. So guess what I have to do? This is going to be my x, y, and z, or my vector r, and I'm going to solve for t again, and I want to make sure all my t values are the same. So here we go. I'm going to use the parametric form. Y, it's a nice, easy setup for me. I'm just going to replace x with 0, y with negative 15, and z with 9. So let's do the x first. So I'm going to have here 0 is equal to 2 plus t. Well, this is easy. Bring that guy over. Negative 2 is equal to t. All right, done. So that's my x. Let's look at y next. My y is negative 15 is equal to, now I'm going to go over here, negative 1 plus 7t. So bring this over. I get negative 14 is equal to 7t. Oops. T is equal to negative 2. So far, so good. Checked out. Let's do the last one. Well, the last one is z. So here I'm going to have my z value as 9. So I'm going to have 9 is equal to 5 minus 9t. This is not looking so promising. Bring this over. I get 4 is equal to negative 9t. And unfortunately, it is not equal to negative 2. These two are. This is not. All three have to be. So therefore, since all t's are, are not equal, the point 0, negative 15, and 9 is not on, line 1. That concludes lesson 1.